Jai Hind. Hello cadets. Now let's continue our discussion with the next type of telescope, that is the terrestrial telescope. Now this is another refracting telescope that we will be discussing right now. So the basic, or we can say the fundamental working of this telescope is very much similar to that of astronomical telescope, but there is an important difference between these two. In case of astronomical telescope, the final image is inverted and it doesn't make any difference for us. So imagine you are looking at moon and it appears inverted. When seen through a telescope, it doesn't make any difference to us. Now suppose you are using the same telescope to observe a distant object on Earth. It's called a terrestrial object. Now, when you see any terrestrial object, in that case, the final image appears to be inverted. For a terrestrial object, it is not at all acceptable to have an inverted final image. And that is the reason that apart from the objective and the eyepiece, one more lens is used in a terrestrial telescope with the sole purpose of producing an erect image. So apart from this one extra lens, everything else in the terrestrial telescope is just like it was in case of an astronomical telescope. So starting with the arrangement of lenses. So there are three lenses arranged in a coaxial manner, with largest of all being the objective lens. So consider this is an objective lens through which the rays of light from the distant object will enter. Now, for this lens, again the image formation is the same as before, that is object at infinity, image at the focus. So, parallel rays from a distant object will be incident on the objective lens. From here, those rays will converge at the focus of this lens and we will have a real but inverted image of whatever distant object that we are looking at. Now, at a suitable distance from this first image, one more lens will be there somewhere at this position. The distance of this lens, the position of this lens will be selected such that for this lens, the image formation will be object at 2f, image also at 2f. Now, if you remember that image formation produced by a convex lens, then you will remember object at 2f, image is also obtained at 2f, it is real, inverted, but the size of the image is same as size of the object, which clearly means that this lens does not contribute anything towards the magnification of the whole apparatus. So whatever magnification this whole setup might produce, it may be because of the objective and the eyepiece, but this lens, the extra lens that we are using, it is not contributing anything to the final magnification or any improvement in magnifying power. Its sole purpose is to produce an erect image. So in this case, for this lens, object at 2f, then the image is also produced at 2f. It is real, inverted and of the same size as that of the object. So this is where this image will be produced. So because of this particular application, this kind of use, this lens is described as the erecting lens. This lens is described as erecting lens. So the objective lens produced an inverted image. The erecting lens produced an erect image, and now after this there will be the eyepiece. if you consider this whole setup where final image is not at infinity, final image is not at infinity, it is at some finite distance, then the refraction through this last lens, that is the eyepiece, it will look somewhat like this. So rays of light going in like this, and finally you will be getting a virtual erect and magnified image using this lens somewhere here. It could be beyond the objective lens also, it could be between the erecting lens and the objective lens also. It all depends on where these dotted lines actually converge. So this is how you will be getting the final image. Once again, because of its use, this lens is called as the erecting lens. So in this setup also, if you consider the magnifying power in normal adjustment, which is minimum, it is still equal to FO upon FE in normal adjustment. Now, if you want to consider what should be the total distance between the two lenses, objective and eyepiece, then first, remember this distance is equal to FO, focal length of the objective. Next, now for erecting lens, object is at a 2F, so this distance is twice the focal length of the erecting lens. Likewise, image is at 2F, this distance is also equal to twice the focal length of the erecting lens. Now, if you remember the astronomical telescope in normal adjustment, the distance between the objective and the eyepiece was FO plus FE. If you use this telescope, that is a terrestrial telescope in normal adjustment, then the distance between these two last end lenses, objective and eyepiece, it will be increased by how much? This plus this, that will be 4 times focal length of erecting lens. So if you consider the normal adjustment, this case only, the distance between objective and eyepiece, it will be equal to FO plus FE plus 4 times of focal length of erecting lens. So because of the use of erecting lens, the total length of the optical tube, the tube that contains all of these lenses, the total length of that tube increases substantially. To be more precise, it increases by exactly this much amount. So, some of the common examples of terrestrial telescopes are a binocular, a monoocular, also called as a spotting scope, then the scope that is there on top of a sniper rifle. All of these are examples of terrestrial telescope because they are used to observe terrestrial objects, objects which are on the Earth's surface, and therefore it is very necessary that the final image obtained is always erect, not inverted, erect. So for normal adjustment, the formula still remains FO upon FE. The only disadvantage is the total length of the telescope, the total length of the optical tube is much larger than that of the same type of astronomical telescope. Okay. Now, in the next video, we will see how this all is taken care of in a set of binoculars. Okay. All right. Thank you very much.